Let us now look at implementation of logical functions with only NAND gates. It turns out that the NOT, AND, OR operations can be realized by using only NAND gates. And let us look at these one by one, starting with the NOT operation. So here is the implementation. We have a NAND gate here. We connect the two inputs together and connect our input variable A over there. So what do we have at the output? We have A dot A bar, and since A dot A is nothing but A, we get A bar at the output. Here is the implementation of the AND operation, and let us see how it works. We have one NAND gate here, so at this point we have AB bar, and then we have connected this inverter. So therefore we get at the output AB bar of that, and that is nothing but AB. So that is the AND operation. And here is the OR operation. This is an inverter, the same as this one. So we have A bar here, B bar here, and then we have A bar and B bar and the NOT of that, like that. And that, by De Morgan's theorem, is nothing but A plus B. So that is our OR implementation. Let us take up this exercise. Implement y equal to AB plus BC D bar plus A bar D using only NAND gates. And as we have seen in the last slide, this is how we can implement the NOT, AND, and OR operations with NAND gates. So for this function, what is our step number 1? Step number 1 is to implement this OR operation. And let us assume that we have gates available to us, NAND gates available to us with 2 or 3 inputs. So this is similar to this A plus B operation here, except we now have A plus B plus C because we have 3 terms, and that would be A bar dot B bar dot C bar and the bar of the whole thing. Alright, so let us write this in this format, like that. So this AB can be treated as A, and since we have A bar here, we have AB bar, and the same thing applies to these terms as well. So that is our first step, and that is the implementation of the first step. So we have AB bar here, BC D bar of that, and A bar D bar of that, and all of those are applied to this 3 input NAND gate. That should give us our output Y. And now we need to figure out how to generate each of these. How do we obtain AB bar? That is in fact nothing but the NAND operation itself, and therefore all we need to do is to connect a 2 input NAND gate here with inputs A and B, like that. What about this term? We have BC D bar and the bar of that. So this can be achieved using a 3 input NAND gate with inputs B, C and D bar, and D bar can be obtained by using this equation. So we use a NAND gate with inputs D and D. So that is B, C and D bar, and D bar has been obtained with this NAND gate by connecting these 2 inputs together and then connecting that to D. And this term can also be implemented using a NAND gate, a 2 input NAND gate with inputs A bar and D, like that. So this is A bar and this is D, and again A bar has been obtained from A using this NAND gate. So this is our overall implementation of the logical function Y using only NAND gates. Next example, implement Y equal to A plus B plus C using only 2 input NAND gates. So now we have this restriction. We can use NAND gates with 2 inputs only. Alright, and here are our equations once again for implementation of the NOT, AND and OR operations using NAND gates. Here is our step number 1, and what we have done here is we have grouped this a plus b together. So we are treating a plus b as one entity now, and let us call that x, for example. So we have now y equal to x plus c. And how do we implement x plus c using NAND gates? We can refer to this equation here. So x plus c would be x bar dot c bar and bar of that. So that is how we can implement this first step. So c bar and then a plus b bar and the NAND of that. Now let us see how to generate each one of these. C bar is easy to generate. We just need to use this equation. So we use a NAND gate, connect the two inputs together and connect that to C to get C bar. What about this operation? This is the NOR operation and it is not there in this list. So what we will do is we will generate a plus b bar from a plus b using the NOT operation, like that. So we have a NAND gate with inputs tied together. We apply a plus b here and then we get a plus b bar over here at the output. And now we know how to generate a plus b using this last equation, and that completes our implementation.